It's my pleasure to. So we are here in a lab. These are like lab talks, and we live stream people to our laboratory. We have lots of PhD students here attending, and it's my pleasure to introduce to you Erik Reinhard. He is a scientist at Technical Research and Innovation in France. He was scientist at several European and American universities before, and most of you probably know him from several books that he authored or co-authored, like High Dynamic Range Imaging, and he also contributed to the standard textbook that we use in our computer graphics class by Peter Shirley, Fundamentals in Computer Graphics, and several other books. So he is probably one of the most innovative researchers when it comes to high dynamic range research. And that is what he's doing in Technicolor now. And the title of his talk is Simulating High Brightness on Standard Dynamic Range Screens.
All right. Well, thank you for your kind introduction. It's a pleasure to be able to do this. I find the concept of doing this over the internet quite clearly an interesting one, because it allows to give talks anywhere in the world, and I can have my cup of coffee by my side. This is fantastic. So what I would like to do is to talk to you a bit about a little project that I've worked on in Technicolor, and it's really only a little project, and it will give you a flavor of how perhaps industrial research is also a little bit different from academic research. The solutions, I have to apologize upfront, are perhaps more ad hoc than you'd think. So I'm now trying to share my screen. I hope you see my title slide. Does this look like a bit of sea with some beach?
Yeah.
Good. Then I have successfully shared my screen. So we have a variety of business units. One of our business units is trying to license patents and ideas and also technologies to display makers, set-top box makers, anyone who makes images and displays these images in people's homes. And this also includes the mobile market. And the question at some point came, they say, well, we've now been working on high dynamic range imaging, and we see that the market will have high dynamic range displays coming. Indeed, you can buy them now. But what for mobile screens or tablets? They are becoming brighter, but there's still battery in them, and you would really want to make sure that your display is not consuming too much power. And obviously, if I make my display brighter, you'll end up using more power. So the question then was, can we do some kind of image processing that simply fakes it? We want to make an image that looks brighter than it really is. Can it be done? And that was the brief that I got. And I started thinking, in a way that seemed to be different from what the business unit was thinking. What I understood was that they wanted to simply increase the contrast somehow, maybe the global contrast, maybe local contrast, but somehow. And I was thinking, well, sure, I can think about that. But if you look at any TV that exists, there's already a contrast knob on it. Why would I invent a contrast knob that already exists? So I was thinking maybe we can do something else, and that's really which gave rise to this specific project. So, that's my title slide, and wait, I need to do some clicking. Maybe I can hide this. Yes, and here's the introduction. Yes. So the reason that you cannot do this on mobile devices really is that the battery life might be compromised. We cannot just expend an endless amount of energy. But also you have to think about new display technologies, quite possibly. For instance, printing, for instance, e-ink technologies. These are reflective technologies, and you will not be able to make that HDR unless, of course, you do something special. But I remember that. I think I remember the research whereby you can put a projector on top of such technologies, but then you still have a dual modulation solution, and perhaps for mobile devices that out in the fields that may not be appropriate. So the question is, can we fake it on a mobile device? We want an SDR screen or to be as bright as possible. So I looked at the design constraints, and I thought that this would be a reasonable set of constraints. First, we want to process an image, just a standard dynamic range image, in such a way that the visual quality ends up being closer to that of an HDR image displayed on an HDR display, except that we don't have an HDR image and we don't have an HDR display. Further, because I work for Technicolor and we work with producers and directors, we want the director's intent to be substantially preserved. So the image should really still tell the same story. And how you measure that, well, I don't really want to go into that, but for us, director's intent is sacred. We provide post-production services for directors, and we need to deliver to the end user what the director wants and not something else. Further, we don't want artifacts to be introduced. If someone says, that image has an artifact, why did you do that? Then we've made a mistake. And of course, we assume that a mobile device will continue to have an 8-bit bit depth. If it increases in the future, that is a bonus, but we're not counting on it. And of course, the peak luminance would not be higher than what we normally consider standard dynamic range. So 50, 100 candela per square meter, something like that. And then, of course, you would want this to work on video, so temporal coherence should be maintained. I've not looked at that for the purpose of this project, but who knows in the future. And it should be real time eventually. And of course, my solution isn't, because my feeling was, let's test first if this can be done at all, rather than try and begin by making it real time. So how can we do this? Well, let's summarize our research question first. So we want to. So this is a management slide, because I've be showing this to managers within Technicolor, and you need to tell them precisely what the method is and isn't, and what it might do and where it will fail, because otherwise they will expect absolutely everything. So my summary is, we want to actually make the image look brighter, but at the same time we want to preserve the director's intent. So we actually don't want to change it. So how can you change an image and not change it at the same time? Well, you can't. So there are conflicting goals here, and therefore I've been telling our managers in red that there's going to be trade-offs. Very important if you work in industry. So then I looked at, so what is it that makes an HDR display different from an LDR display? And of course, if you just look at the features, you might find that an HDR display has a lower black level, especially with OLED displays. You might find that the peak luminance is higher. Now, you will find, because that's more or less what defines an HDR display. You might find that that global contrast is higher. Of course, the highest, the brightest bright and the blackest black will be spaced out more, of course. And then one thing that is kind of important is that an HDR display will cause glare. Glare is really no more than light scattering in the oculus, in the ocular media in the human eye, and that glare happens as soon as you open your eyes, but of course it becomes more visible if there are brighter sources. And of course, in an HDR display, the sources are brighter, so you will have a little bit more glare to deal with. And well, there's other attributes that are near identical between HDR and LDR displays. Well, the first is local contrast. Because normally, if you look at an LCD backlit display, the backlight is low resolution. That means that two neighboring pixels cannot be arbitrarily different. It depends on the backlight. So local contrast is really not so different between an HDR and an LDR display. And perhaps this sounds strange, but if you look at the mean luminance of material that is displayed well on an HDR display, if you make an image that looks good on an HDR display, you find that the mean luminance is not so much higher than on an SDR display. It's really the brightest pixels that are very significantly higher. So, of course, if the differences are nil or very small between an HDR and an LDR display, then these are things that you cannot really change and hope that you get an LDR image on an LDR display to look more like an HDR display. So local contrast and mean luminance, we are not messing with that. This does not seem to be a good path. Also, these things tend to change the director's intent. Anyone who has searched for HDR on the Flickr website knows that local contrast kills an image if you increase it too much. So you really don't want to deal with that. If I go from the top here, the black level, well, that's hard to manipulate in software. It really depends on the hardware what the black level is. So I can't make things blacker than they are. That's going to be very difficult. And I've already said before that one of my design constraints was I don't want to mess with the peak luminance. The peak in the image has to be the same as it was before and after the image. And the reason is that I want to maximize the use of the display range that I have available. It is already an SDR display, so I don't really want to go below that. It doesn't even make sense if I want to simulate an HDR on an SDR display. And then, as I've argued before, global contrast already implemented in TVs, and I blatantly refused to implement something that was already there. So that leaves me really with glare as the only thing to look at. And that really surprised my managers, because in essence, glare is seen as an evil that needs to be avoided, rather than actually simulated and added to an image. And in general, I think that if we add glare just everywhere in an image, you effectively help to destroy it. So I wanted to deviate a little bit from what our eye does. So not add glare everywhere, but add it a little bit more selectively in a way that enhances the image without destroying the black level and making the image actually unwatchable. So here, this is a slide I prepared for today. Here you see effectively 4 squares, black on a white background. And if you look at the white square in the middle, you will see that the amount of light that comes off it is the same as the background of the slide. It's just full on white. And I am assuming that you're watching this on a projection-based display. I'm assuming that what you see is more or less the same as what I see, just a black and white image. Now, if I click, then this will slowly morph into a different image. And the only thing that I will have changed in the next image is that these 4 black squares have been replaced with a ramp that goes from black on the outside to white on the inside. So let's start that and see what happens. So there it comes. So takes a few seconds. So what I've done is really I've only changed the black squares, and you see that they now go from black on the outside to white on the inside. But what's also happened is, at least on my screen, I can see that white square in the middle now looks brighter. In my mind, it does. Also, what I see is that in the 4 corners of the black cross, the image now looks darker. But these are all pixels I have not changed. These are still exactly the same. So something in my perception has changed. And in essence, what I think that's happening is that the human visual system expects that our eye is producing glare, and when there's glare produced, it knows that there's something bright. So if that's really just speculation, I have no references for it, but I think that the visual illusion of having a bright square here in the middle is coming from a heuristic that the human visual system applies, which is based on the ocular light scatter that happens in the eyes. So this is really an argument for me to suggest that we might be able to simulate glare in some way and hope to get an image that looks brighter without being brighter. Of course, the square in the middle looks brighter, but isn't brighter than the rest of the background. Anyway, so that's the aim. See how we get there. So now we need to go talk a bit about an algorithm, and this is where I feel that I have to apologize. The algorithm that I've come up with, I think, does a pretty reasonable job. It's reasonably robust. It's also reasonably fast. It's not real time, but reasonably fast. So it fits with the design brief almost. But as a consequence, I have concocted effectively a monster. It's an algorithm that is not particularly elegant. And it is more than a little bit ad hoc, and especially the ad hocness is what sets this apart from academic research. This is made to create something that works for a specific use case. It is not meant to teach and inform and contribute to a body of research that stimulates follow-on research. So for that, I apologize, but I can't make everybody happy. I have first and foremost these days a boss to make happy, and the priorities are a little bit different. In any case, the glare simulation. So the idea is that I want to use pixels in the image as a glare source, but not all the pixels, because if I use all the pixels as glare sources, I just smudge everything, and that is not a good idea. And then second, I don't really want to apply the glare everywhere, because that also creates more problems than it's worth. So with these constraints in mind, what I've ended up doing is creating a sequence of steps where filtering is applied, followed by some luminance remapping, very simple functions, followed by more filtering. So it's an alternation of filtering, remapping, and then that's essentially it. The choice of filters, of course, is a little bit important. The choice of remapping is ad hoc and perhaps only a little bit important. So there's only 16 steps in this method, but of course some of them are more simple than others, and certainly the first three are quite straightforward. The first one is, well, it's really an effect that is best applied to luminance, even though we do also do a small chroma adjustment at the end. But because of that, it makes sense to choose a color space where we have something that looks a bit like luminance. Now, CLab has that. In fact, their L channel is lightness. And because it's lightness, it's effectively a nonlinear function of luminance. And I wanted to calculate on luminance. So I have therefore added the second step, which is effectively undoing the linearization of CLab. Of course, if you implement that, you would simply not go to the non-linear space to begin with. Third step is also trivial. It's the maximum in the image. I want to know, typically, that would be 255. That's what makes sense. But it helps to normalize everything and make everything a bit robust. So this is relatively straightforward, I hope. After that, I want to effectively select the pixels that are going to serve as glare sources. And for that, I simply take the luminance image, L, I normalize it, and then I apply that function that I've plotted at the bottom. This is almost a threshold, but it's almost a threshold, but not quite. And that basically selects only the brightest pixels, and it selects them according to this remapping function. So it allows a little bit of feathering near the edges of bright sources, and it helps smooth things over a little bit. That's the reason for doing it this way rather than having a hard threshold. So this is not too difficult yet. So then the effect of that is shown here. On the left, I have an input image. And on the right, I have that remapping step visualized. So you see everything that's bright is selected. Everything else is pretty much black. I call that in the rest of the presentation a mask, but really it's not a mask in the true sense of the word, in the sense that I see a mask as something that selects pixels that can, in the original image, that can then be used for processing. Here, we simply compute directly on the mask itself. Of course, this image on the right we can now use to calculate glare. So that's precisely what we'll do. First, we need to determine, once we have calculated the glare, how much of it we're going to add to where in the image. So for that, this is exceedingly ad hoc. We have another remapping function that will tell us how much glare is going to be added based on the pixel value that we want to add glare to. So little function, it effectively adds little for bright pixels and a lot for dark pixels. Very ad hoc. The shape of this function, as you can see here, is well, it's not a completely smooth curve. There's a little bit of a kink near 0.05, I would say. Don't think anything of it. The reason it looks like this is because I was impatient. All my remapping functions are implemented with little spline functions. That was easy and quick. And I've tweaked the parameters of it by eye. So there's nothing principled about this. If I remove that kink and make a slightly different curve, it would do exactly the same job. So this is not critical. The next step is, well, we need to compute glare. So we need to convolve the image with a filter kernel. And on the left, you'll see a kernel that more or less looks like a glare filter kernel. And in fact, it's a glare kernel that I got out of a paper. And I'm sorry, I have forgotten which paper it was. It's again not critical. If you take your favorite glare paper, you just you implement the filter, and then it will look something like this. It is, however, important to notice that a glare filter typically has a very sharp spike in the middle and then a very steep fall off, but it's also a very broad effect. There's the filter kernel is non-zero for quite a large area. So of course that makes convolution a bit expensive because all these small values actually do matter for adding glare. And that means that if it's expensive, we will not be able to implement it in simple hardware. Thinking set-top boxes, I'm thinking televisions. So if you do that, or indeed mobile devices, if you try to convolve an image with such a large kernel, you'll spend a lot of time. So we also experimented with making such a kernel separable, and what you see on the right is the separable version of K. So we did that through singular value decomposition. This is a standard technique. And you'll see that it's only an approximation. It does have far too much energy in the horizontal and vertical directions. So this is really not a very good kernel, but under circumstances you might be able to get away with this. And of course, now it's separable, the convolution can be made separable, and it'd be much quicker to calculate. So we typically do step 7 for speed. If you do that, and you do that on the mask image that I've shown you earlier, then you get the image on the right, and that is effectively an image that looks a little bit blurred. It's just that the blur was not Gaussian. It's a glare kernel that was applied here, and that's the basis of further processing. So what do we do with it? Well, we first reshape that image so that the large values are only where the input image was dark, and that really is to avoid glare, adding glare to image areas that are already bright. Remember, we have an 8-bit image as input. The budget is well a maximum value of 255. We will go over a little bit anyway, but we don't want to overdo it. Yeah, that's how we've designed it. Of course, all my images are shown normalized, so that's why you see an odd reversal between the input and the output image of this last step. What we do notice, though, is that as a consequence of the convolutions followed by the remapping, near the edges, if the image edge is not perfectly sharp, what we then have is a little bit of fall off from bright to dark in the input image, but we have a rise in value in the convolved mask, and they meet somewhere in the middle if you composite that together. And the problem with that is that we introduce a false edge. And this false edge is, of course, visible and problematic. I found an ad hoc solution again by simply convolving the image for a second time. And then what you see is the result on the right. And it's the same filter, just applied on the previous result one more time. And with the remapping, you see what it looks like on the right. So that starts to look like something we can add to the image to simulate glare. We're not completely there yet, but we're getting there. The next step is to reduce a little bit of contrast. So far we've only been remapping luminance itself. There's benefit in also reducing the contrast a little bit. This is really from personal observation. If you look at a strong glare source just around it, you will find that light is added. It's an additive process because of the in-scattering in the ocular media, but the net result of it is as well that the contrast near a glare source is reduced a little bit. And so to help things along a little bit more and make things look a little bit more realistic in our faked images, we've decided that perhaps we can also reduce the contrast a little bit. And through another sequence of ad hoc convolutions and remapping, the remapping function you see here, so it's only a very, very slight attenuation. And the Gaussian, the convolution this time is with a Gaussian filter because we're now just looking at reducing contrast. This will give us just that little bit of reduction in contrast, and I'm really not even sure that this is very visible in the images that I'll show you. Nonetheless, on a big television screen, I could just about see the result of this, and I thought it looked a bit better. It's clearly a step that could also be omitted. So this is the Gaussian blur applied to the image. And then after the remapping and the compositing, we'll end up with this image. And then we're nearly there. So we have that remapped image from the previous slide. We have the glare simulation, we have a weight factor, we combine everything, and then we go back to our nonlinear CLAP color space to do a little bit of chroma processing, and after that we'll be finished. So really we have a contrast reduction and a glare source added so far, and that's the two terms, and they're weighted one relative to the other through that weight factor W. So that's all that's happening here. So the next somewhat ad hoc step here is that we know that lightness and chroma are correlated in human vision, and we have just messed with with luminance. But of course, if you mess with luminance, you're also messing with lightness. We've converted to nonlinear CLAP space, so the L channel, because it's now not linear, it's representing a sense of lightness. So, because they're correlated, we've changed lightness. Now we need to change chroma. Chroma is easily computed out of the A and B channels in CLAP by taking the square root of the squares of A and B. That is again a standard technique. And then here is probably the most awful remapping function I have ever come up with, and I'm not proud of it. It is entirely ad hoc, and I'm actually fairly ashamed of this. What we figured out is that the glare source that we've calculated, the chroma that we've just calculated, and the lightness that we have now can be remapped according to the functions that you see here, the red, green, and blue lines, for glare, chroma, and lightness, respectively. And if you do that, that gives us, in essence, a term that we can subtract from chroma itself, as indicated on the previous slide. And that reduces chroma in the areas where there is a lot of glare, and of course it doesn't do much to chroma when in areas where there isn't a lot of glare, and of course that is desirable. If there's no glare added, we also don't want to mess with chroma. That I think makes sense. If we then convert the result to RGB, then you'll see an image that looks nothing like a good image. The thing to remind or to remember here is that we have effectively added a glare source to an image. Of course, the original image was already going between 0 and 255. So somewhere in this image, we've gone beyond 255. And I'm displaying my image here in a normalized manner. So as a consequence of that, the whole thing has become a bit darker due to the normalization. Of course, all the information is still in the image. It's just for visualization that this now looks a little bit funny. However, if we clip everything that sits above 255, the good old standard RGB way to do things, then we end up with an image that looks more or less like I had it in mind all along. You see now that this image is not so far from the input image. However, around all the bright parts, there's now that little light halo around it, and I would argue that now looks brighter than the input image did. I will show you before and after results, plenty of them in a minute. What I would argue, though, is that if you remember that cross that I showed you in the beginning, where adding a white ramp on the black parts made the center look more brighter, I think, well, at least I can convince myself that something like that has happened in this image as well. In my mind, but please come to draw your own conclusions. In my mind, the brightest parts in this image do look a little bit brighter than the background of this slide. But it's my opinion, and of course, because we've never bothered to publish this work, I have not done any tests to confirm this across a sample of participants. In a good piece of research, that of course would have to happen. Now, if I summarize some of the features of this specific algorithm, you'll find that all the filter operations are implemented with separable filters. This is good because that makes it faster. All the re-rating was achieved with little spline functions. That was because I was lazy, and it's easy. I mean, if I can design one spline function, I can design 10. It's very easy to do that. And of course, I did this all in MATLAB. Makes it even easier. I've made an implementation whereby there's only one parameter, and that is how much glare would you really want to add. And I've used that parameter with some care, but I did in the results that I'll show you in a minute. I've exaggerated, and that is really to create a wow effect that would be consistent with a really quite a bright display, more than our display would be able to handle anyway. So the performance of this is on just almost HD sized images is about 4 seconds. My colleagues who work in hardware are telling me that that is absolutely unacceptable for current SoCs that you see in televisions. It's also not good enough for the little graphics cards that sit in set-top boxes. But perhaps next generation set-top boxes can handle this. So while this is not implementable in these simple hardware scenarios now, I think it will be soon enough. And on that basis, my boss has agreed to patent this. Yeah. All right, so we need to look at some results. I have here first a section of results that I've created with fixed parameters. That works for quite a lot of images, but not for everything. So after that, I will also show you some results with where I've actually tuned the results effectively to my taste. And then I have one conclusion slide at the end, and then we're done. So we're not so far off. Wow effect, yes. So I've already talked effectively about everything here. So I'll skip this. So here's the input image in full screen. I have for each of the inputs and outputs, I put the word input and output on screen so you can tell and compare. I will go back and forth now a few times. So here's the output, here's the input, the output. And the thing to notice, of course, is that that quite a large part of the image has not changed at all. The closer you get to the light sources, more and more change starts to happen. And I would argue, and I think at least some of my colleagues agree with me, that the output image does indeed look brighter, even if I haven't increased the peak luminance, I haven't changed the black level, I have not changed local contrast in most of the image. In fact, all I have done so far, or in this research, is I have deteriorated the image near the brightest parts. Here's another result. After, before, after. My feeling is that in this case, there's not so much to do. And indeed, the combination of steps that I've implemented was designed that in a case like this, where there's expect all that much glare to happen in the first place, the effect is not as dramatic as in the first result. Here's also one of my favorites. This is quite clearly a good candidate for adding glare, and if you do that, it will look like this. And I would argue that this now looks like there's more light streaming in from outside than here, without changing the image so much that you would say, oh, that's a different image, or even without saying that this is an obviously processed image. Of course, if you see them before and after, you will clearly notice the difference, and you will know that this image you see now is processed. However, if you hadn't seen the input image, I suspect that you would accept this image as a plausible image. you wouldn't instantly doubt that this was a natural scene that had not received any processing, and that is the purpose of this research. Here's the result. You see, fairly subtle in this case. Of course, there's many images where there's simply not much to do. Some images, of course, benefit more than others. And, this is, for instance, one. Some images didn't do enough, in my view, on the standard parameters. So we had to I had to bump it up a little bit. Here's an example where I've tuned it to taste. So this is not with the standard amount of glare added. It's either more or less. I'm afraid I can't remember precisely which direction I went. Here there's some bright chrome on the bumper that can be enhanced like so. I find also an interesting image. This is an image that clearly has already glare in it from the capture. So this was an interesting test case because the question is, can I add more glare and will it still look like a plausible image? I think perhaps it does. Here's the result. And of course, this is manually tuned, so this is according to taste. It's obvious that your taste may be different from my taste. I would be happy to respect that. So we're getting towards the end. Yes. Some glare on the highlights. Reasonable. And finally, glare around the light sources to make it look a bit more bright. I think that was the last one, so I'm up to my last slide. So I will not claim ever that this method will set the world on fire. It probably won't, but I think it's an interesting tool to have in your toolbox if you want to simulate brightness on displays that simply aren't bright. I also think that that by weaseling it in the way that I've done, I've made it fast enough for interactive use. Maybe there are other ways to do that. Maybe there are better ways. I would not be surprised if there were. We're perhaps one generation away from being able to implement this on next generation systems on chips. But it's currently a bit difficult because the filter kernel sizes have to be large. You see that the glare extends over a good portion of the image. That means large filter kernels, which means expensive to implement on hardware. That is roughly the state of things with this research, and I'm quite happy to leave it at that and see if you have any questions based on this. So thank you for your attention.
So Erik, I think this was one of the coolest talks we had this year. Very interesting and very illustrative, and I was very surprised by the effect. Any questions on your side? No.
Yes, so you mentioned, so I was also really impressed by the results you achieved. And you mentioned that you can change or tune the glare factor. And so like how big the glare is in the image. And does this depend on the scene, or how would you decide what's the best setting for this factor is?
Yeah, so I've done this the industrial way. I have looked at a fairly large set of images, about 100 or so, and for the fixed parameters, I've simply tried to get the parameters that on average looked the best possible, and of course that means that by setting a parameter in a certain way, it works for maybe the majority of images in a decent kind of way, but in other cases it just doesn't work at all. It either does too much or too little. I've not seen cases whereby there are other problems. I've not seen cases where that were different from either too much or too little. Having said that, I did try to, there's interesting test cases in my sets, like a close-up of a white flower. Now, a flower is quite clearly not as strong a glare source as a light source itself is. But the pixel values in an SDR can be the same, right? A white flower will have values certainly above 200, but perhaps close to 255. Light source also sits around the same range. So how can you now make something that does the right thing on the flower, but also the right thing on the glare source? And so it's these trade-offs that I've looked at carefully, and it's also one of the reasons that all these remapping functions look a bit weird. That probably does not answer your question, but this was anyway my effort.
No, it does. Thank you.
Okay.
More questions?
Did you actually think about learning this transformation? Because now, I mean, image processing, all these convolutional networks are really popular and they can do really interesting things. As Adobe often has a really interesting papers for image processing, or was recently one where they improve night images to make them look more vivid. So that you just then create a training set by just applying your transform on a big data set of images and then running a convnet over this, and then that you actually then get it faster via then just learning this transformation.
I think that's quite clearly the route to take if you were to do this now. So what I can explain about this research is it's not published, it was not presented before either. This was really my first external presentation of this. But it was done already a couple of years ago. At a time where I was certainly not looking at neural networks to solve problems. I am looking at these things now for other reasons, and I would agree with you that if I had to do this project from scratch today, I would probably look at that very seriously to see if a network can be trained to do this task, and that might be more robust. It might be. But then it might not be. We know that there's still various problems with neural networks, especially since you have to synthesize a full screen or large size images. When neural networks need to synthesize or reconstruct an image, if you do it with GANs, for instance, that tends to be difficult to control for the moment. In a few months from now, that may all look completely different again. I don't know, but at the moment, I think a solution for adding glare in a sensible way can probably be constructed with a neural net. But I'm not sure that the reconstruction is quite there yet. I think it will be soon. This field is moving very fast.
Thanks.
More? So I have a couple of questions, Erik. One is the question that is the point spread function of glare depth invariant? The other question would be, is it okay to use a constant size filter?
So I don't know. So it's in essence a simulation of a process that happens in the eye, and I don't think that that once photons enter the eye that it matters from how far away they came. So I'm not considered making this somehow dependent on depth.
Because through the pupil, and I guess the pupil as an aperture would have different point spread sizes for different point distances, right? So I don't know. Not sure. That's really a question.
Yeah, I'm not sure that how that would work. I think the pupil size is mediated by the amount of light,
Yeah.
but not on the distribution of light.
Yeah.
I forgot your second question. Could you possibly repeat?
Because you're using a constant size filter current, and of course, if the glare point spread would be variant to that, then you would scale. You would need to use different scales of the kernel for your.
Yeah.
At the moment, you use only a constant size kernel, and that would assume that glare is step invariant, which it might be. I don't know.
Yes, that is the implication and the assumption under which I worked. Of course, the size of the kernel needs to be tuned for image size and also display size. I've not made it flexible so that it can handle different image sizes. The kernel I implemented was simply for images the size that I had lying about, which was 1660 by 1024 or something like that. If you go to 4K size image, you would have to adjust.
But it's constant for every pixel. That's the point, and that assumes that glare is depth independent.
Yeah, I've made it constant. I would have to think a bit more to see if I wanted to make it non-constant, to see what that would mean and how I would organize it. At least for us, this would complicate the algorithm further, which would have an effect on the computational time, and I somehow suspect that that moves it further away from hardware implementation, at least for the moment. I'd be interested to see what can be done with this.
But if you look at physical glare in the camera, then you pretty much probably would see it if you have a point source at different distances, if the amount of glare in the image changes or not. I really don't know if that is.
Absolutely. If you have a depth camera, then that could drive the calculations quite easily. Yeah.
The other question I had is because you mentioned you don't know where this effect comes from or why we perceive this. When you showed the first image with the cross, if you can switch back to the slide with the cross.
I can try. Let me. And I need to share my screen again. Up, share.
And
There it is.
The second with the glare.
Yeah, I will try and put that on.
What I thought when I saw this for the first time is that this is a simultaneous contrast effect. Do you think so? Because what I also see in the white square in the center is at the edges, in the inner edges, that tends to be become darker. It's perceived darker. So the edges of the white square are brighter, but if I go towards the inner side of the white square, right after the edge, it appears darker. And to me, this looks like a simultaneous contrast perception effect.
I think it might be.
Yeah.
I think it might be. So I'm not. I'm only speculating. I'm only hypothesizing that there is a link between the visual illusion and the ocular light scatter that happens. I don't know that that's true. I don't know of any research that has looked at this. It's also possible that that what you see here is purely a neural effect and is not made stronger because the eye scatters. So it's certainly a contentious statement I made there, and other opinions are quite clearly possible. I don't have proof for the link between this visual illusion and the occurrence of glare in the eyes.
It just looks like simultaneous contrast because I would not otherwise be able to explain why actually the white cross becomes darker towards the center or appears darker towards the center. It's only the edges that appear significantly brighter than before. You know what I mean?
Yeah, I do know what you mean. Yeah, I'm not sure that I have a good answer for it at this point.
Okay, any more questions? Going once, going twice. And Erik, thank you very much for this very cool and interesting talk and project. Thank you.
It's a pleasure. Thank you very much. Bye-bye.
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 That's it for this semester. Summer break comes up next, and we'll see who is going to speak in the next interview. Bye-bye, Erik. Thank you.